Hello everyone. Today we're going to solve the following vibrations problem. You're given a graph of position against time of a vibrating system. It consists of a 20 kilogram block that is attached to an element that has been displaced for 1 centimeter and then released. The resulting oscillations were monitored and the results are shown in the graph. We're asked to determine the stiffness coefficient and the damping coefficient for this element. So the way that we do this is that we start by calculating the logarithmic decrement. It's equal to the natural log of the position divided by the position 1 period later. So here, for example, we could take x sub I is equal to 0.01, which is this value over here, and then 1 period later brings us to the following peak. So x I plus 1 equals about 0.05. I'm sorry, 0.005. Which gives us 0.6931. After that, we're going to calculate the damping ratio. We're going to calculate the damping ratio as a function of the logarithmic decrement that we calculated before. We get 0.1096. It's unitless. Now we're going to calculate the damp natural frequency. So it's omega sub d is equal to 2 pi over the damped period. We could have calculated this before since all the information that we need is already readable from the graph. So the damped period is the time that it takes to go from peak to peak. And so this is T sub D, and it's equal to 0.06 seconds. All right. Also, these are meters. But it doesn't really matter because here this is unitless. So we get 2 pi over 0.06 seconds. And this gives us 104.7198 radians per second. Next, we're going to calculate the natural frequency. We have a formula that gives us the damp natural frequency as a function of the natural frequency times the square root of 1 minus the damping ratio squared. And so we get an expression for the natural frequency. The natural frequency is always higher than the damp natural frequency, and in this case it's equal to 105.3545 radians per second. We're in pretty good shape because now we can calculate the stiffness. We know that the natural frequency is equal to the square root of the stiffness over the mass. Oops. And so the stiffness is equal to the mass times the natural frequency squared. That's 20 times and that's equal to 2.2199 times 10 to the 5 newtons per meter. That's one part of the answer. Next and finally, we will calculate the damping coefficient. We know that the damping ratio is equal to the damping coefficient divided by 2 times the mass times the natural frequency. And so we get that the damping coefficient is equals to 2 times 20 kilograms times 105.3545 radians per second times the damping ratio, which is 0.1096. And so finally, we get a damping ratio, coefficient, of approximately 462 newton second per meter, which is the second half of our answer. In a following video, we're going to solve this problem using a different method. If you'd like to have this sheet as a PDF, I've put a link in the description below. Thanks for watching.